Okay.
Hello, Sky, and thank you very much interviewing me today.
It's my pleasure. I think we met in 2014, right? Yeah.
Right.
And you have been following my research?
Yeah, exactly. We met in 2015. Yes, I met you in a library, which is in the Shenzhen library, which
Yeah,
is
that's
not
right.
surprising. And at this time, I remember you introduced me the beginning of your book. It was the first version. It was
Yeah, it was
already
like
finished.
50 pages. Yeah. And
Yes.
now it's almost 700 pages.
And just for remember this little detail, I came here. It was just 2014. I came from England. I'm French, but I came from England, and I was living and working with some researcher in physics, and we had topics actually cosmologists. So we had already topics about that. We didn't know each other before, but I spent like 10 years with them. And I was really glad to meet you in Shenzhen and again on these sort of very, very interesting topics. And to see
You
that
still remember what the age of the universe is according to my theory? It's a very special number.
maybe not, but billions of years, I guess.
42 trillion
70
years. Yeah, you know the number 42 is
42
very
or,
important.
or very old then, more older than. Yeah, so you have a theory that is has some different aspects than we are used to.
Yeah, so you
That
don't
is
need
very
dark
interesting.
matter and dark energy. If the universe is very old, then it's very natural that everything is burnt out and invisible. So the only reason
Yeah.
to assume magical dark matter is to believe that the universe is very young, when it really is very obvious to me that it's very old.
Yeah, and then you need to add the dark matter and dark energy, and we haven't really observed it. So yeah,
Yeah,
I
nobody has ever
understand.
detected it. Yeah. And you know what my current project is about?
Yes, now you have done a long way, as I remember, as I recall. We can we could talk about all this another time, but it's a lot of work.
Yeah.
And
So
right
this is
now you
about a
are
material analyzer. Yeah.
yeah, right now you are it's related to some chapters of your book about the gravity and mass. Yeah.
Yeah. Yeah.
Measuring the
So
distance, but
in the
measuring it.
mainstream, gravity depends on mass or energy. And so Newton said that it depends on mass, and then Einstein later generalized it because mass and energy are equivalent. And
A
so
different
mass there
scale.
depends on energy. Yeah. And I say that both are wrong, and it actually depends on the number of particles.
Yeah, that's great.
And because different materials have different amounts of binding energy, and binding energy is negative, so that reduces the mass, but it doesn't reduce the number of particles. So you have more particles per kilogram for iron, for example, compared to water.
So your theory of gravity is closer to the theory of electromagnetism, because in electromagnetism, things depend on the number of
Yeah, on
particles.
something that you count 1, 2, 3, 4, 5, more discrete, more natural, more normal. I mean, in all other theories, you have discrete charges, and only gravity you have something like energy
Yeah.
controlling everything, which is very unnatural, and which also makes Einstein's theory very nonlinear.
Yeah, it looks
Because
like people
gravity
don't
also
know.
has energy.
It looks like people don't know they didn't know, and so it's a bit like the temperature. The temperature is a macroscopic measure of actually microscopic activity of particles, and we don't really know, but we make an average from far. But if you look deeper in the thing that you measure, the temperature is not uniform even on the surface of the body. So the temperature just a
Yeah,
number
so
like
it depends on something discrete, but it's different from electromagnetism, because in electromagnetism the sign matters, plus and minus, but here only the number matters, how many. So it's a side effect of the strong force. So in the strong force you have color charge, and that has three different things cancel out to zero. But here I'm not interested in the color aspect, but only into how many color charges are there. So I just count the quarks, or and since quarks always come in protons and neutrons, so I just count the nucleons, the protons and neutrons, and that's what gravity depends on. And so if different elements have different amounts of particles per kilogram, then that means, according to my theory, that they have different amounts of gravity per kilogram. And we can test this in free fall experiments or Cavendish experiments, or pendulum experiments, all of which confirm the theory very well. But on a practical level, we should be able to, and we are able to test what material something is made of by simply comparing the readings of a scale and a balance. You know the difference between a scale and a balance, right?
Yeah, I think you reminded us previously.
Yeah, a scale measures weight and a balance measures mass. So that's because if you imagine a classical balance, like in ancient times, it has weights on both sides, and so it doesn't matter if you measure on a mountaintop or at the beach.
You measure the mass against another mass.
So if gravity increases overall, it doesn't make a difference. And some people are a bit confused by this because they imagine if gravity depends on the material, then you actually could tell differences. But the thing is, nothing on a balance, nothing drops independently. Like this here doesn't drop independent from this. So you have to look at the material of the whole thing on both sides. And so at the end, it really is a good device to measure mass, even in theories where gravity is material dependent. And so if you compare the readings from a scale and a balance, you can tell how much the scale tells you the gravity, the weight, and so you can see for the same mass how for the
I didn't ask you this
materials.
question. This one you call it the balance, right? This
Yeah,
one?
and there are electronic versions of it where you can't see that the balance part. You can't see the beam. It's hidden inside.
Okay. So my question is, have you measured maybe a particle of lead and a particle of I don't know, gold or something else
Yeah,
together, one on each side of the balance, and maybe they are each.
No, I'm using an electronic balance where there are no different sides. This is my balance. It's electronic. There are no different sides to it. The mechanism is hidden inside.
Okay, so you measure only one element at a time.
I use it to measure the mass, and then I use a scale. This is a scale to measure the weight. And so it's confusing because both of them show a mass. The scale will still display a mass, but in reality it should display Newton.
Yeah, because this scale, if you use it on the mountaintop or so, it will give different results.
Yeah, and also when people use scales, they still not interested in force or gravity or anything. They just want to know how much is it, how much mass is there, and so they calibrate it and everything. And so when I have only this, then basically I have to have I cannot use the same mass to calibrate them both, because then I force them to show the same thing, and especially when using a very heavy calibration mass, then basically any slight difference between the calibration of this and this would only show up for something that is much heavier, and this is already the limit for this is 200 grams, so that's 220 would already be the maximum. So basically I have to install a calibration gap so the two show different values, and then I look at the ratio and track how the ratio changes between the display of the mass and the scale, how the ratio changes when we look at different materials. The ratio is arbitrary. The calibration gap is arbitrary, but for convenience, I make it so that it's equal to the ratio between inertial mass and gravitational mass. But anyway, in the final version, this would really display newtons, so I could very straightforwardly have kilogram there or gram there in Newton here, and then could say, okay, this many Newton per gram. And so then people would see it and be surprised, oh, the newtons per gram are different for different materials, which is quite surprising.
Okay.
And
So quite challenges, huh? To
well, it works. It works quite okay now. Like if you want to just have evidence that it's correct, but if you want to prove a point. But if you look at the
yeah.
graphs that I get now, if let's say I measure every material only 3 times or so, I get a graph and it goes up and it follows the curve, kind of, but it's a bit chaotic. It goes up and down, and also a lot of materials, they have almost identical gravitation constant. So
So
if I
you
really want this to be a good product, I need a load cell. Load cells are the things inside a scale that allow the measurement. I need a load cell that measures 0.000001 Newton. And that's possible with a class A load cell. So, but nobody has ever used it to build a scale, but I'm going to do that.
Okay, yeah, that's very good.
They use it to build some machines that test forces on surfaces, some very precise things, material
Try to
testing.
help you with that. Yeah, so you have spent quite a bit of time now creating your experiment protocols, and now I understand you want to refine the experiment procedure to make it like steady, to have a curves that are actually that gives the right hour, that gives the right time, that are not a bit chaotic because of some irregularities. And
Yeah, and
you
at the end
are
it will be doing, you know how difficult it is to do a Cavendish experiment. Only
yeah,
a few people have done it in the last 200 years.
yeah.
And it a single oscillation is 15 minutes or 16 minutes, like when I did it in 2020. And you basically get basically the same thing, but just with a simple scale and a balance. You can compare G values. You don't get an absolute G value, but you know the ratio between different G values. And it's pretty amazing to do something that normally takes a whole year or something to do it in a few seconds.
Yeah, quite, quite
And,
amazing.
and people can know the material a little bit from just submerging something in water to know the density.
Mm.
But then, for example, gold, and this is gold and tungsten, for example, have almost the same density. So you could just take tungsten and put some gold on top of it and sell it as a fake. Yeah, but with my chromogravity scale, that's the name, or yeah, a material analyzer based on quantum gravity, you can know the material without looking at the density, simply by its gravity, by how much Newton force is measured for the same for 1 kilogram or for one mass unit.
And it's a force applied by the Earth, the field, the gravity field of the Earth, or maybe you have another theory. Is maybe
Yeah,
it's maybe not gravity.
the Earth, but the Earth has a different mass also in my theory, so it's ever so slightly heavier, but it's just 0 point something, 0 point.
Yeah, it depends the place you are on Earth, and it depends the altitude. There is a
Yeah, but
there is
also
a
the
point
mass is
I
different
heard.
because the mass that you get in the mainstream is basically the mass that Earth would have if Earth was an iron ball just made out of iron. Also, the mass of the sun
And
in the mainstream
uniform
is
and
assuming
uniform.
that the sun is an iron ball because the G value that they're using was obtained with iron.
Mm,
And basically how heavy the sun is or the Earth is depends on the value of big G. But
mm.
if that is material dependent, then basically what they calculated
Yeah.
is the sun as an iron ball. And so in my theory, the sun is 0.5% heavier than we thought.
How much?
0.5% only.
Wow, that's a lot. And I heard recently, I didn't know that before. It was maybe last week. I don't know why it came to me, this information. There is a place, maybe you know that there is a place in the Pacific Ocean
Mm,
where the gravity is lower than anywhere else, and the people feel very light if they pass there. Some people have taken a boat there, and
yeah.
gravity is lighter than anywhere else on the Earth. But it's
Yeah.
like in the middle of nowhere in the Pacific Ocean. So dare to
Well,
go
I
there.
don't know why exactly that is. So my theory doesn't have anything to say about
Oh,
that. But I think there
they
are some
try to
people who have
explain the
done some
theory.
explaining.
Yeah, they also give I forgot now, but they give some explanation about what is out down there in
Mm,
the volcanoes. They explain that by volcano
mm.
activity with the lava,
Yeah.
and we
Actually,
cannot follow.
my theory also says something about black holes and neutron stars when it comes to gravity.
Of course.
Basically, you don't only have nuclear binding energy that reduces mass, but there's also gravitational binding energy. So the Earth, for example, is 10 to the power 15 kilogram lighter. It has negative mass, basically.
Okay.
So there's mass missing. If you expanded the Earth, it would be heavier slightly. There's negative
Yeah.
binding energy. And for a black hole, it's 30% negative binding energy. And so so the negative binding energy, the gravitational binding energy reduces the mass of a black hole. But according to my theory, it doesn't reduce the gravity. So you have more kilogram per more gravity per kilogram in a black hole in my theory, and that changes the mass of black holes and also the mass of neutron stars. And so both masses change. And so the mass gap that exists between neutron stars and black holes, there's an unexplained mass gap. Like neutron stars, they stop at like 1.3 sun masses or so, and black holes start at 3 sun masses, and so there's a gap in between them. It should be, wait a minute, the heaviest neutron star, yeah, it's about 2 sun masses in the mainstream. So anyway, the gap changes, the gap closes when you apply the masses that my theory predicts. There's no mass gap anymore. Yeah, so we have evidence both from all sorts of experiments on the ground and also astrophysics.
Hmm. Okay. And
Yeah,
so that's it.
yeah.
What what is the most for you? What is the most how to say prominent or and remarkable outcome of your research so far? And that we can measure by your that we can test actually with your experiment.
Um, yeah, basically this, that different elements have different gravitational constants, and beryllium is very low, for example. It has the lowest gravitation constant, and yeah, so you can try wearing something made out of beryllium. Maybe you will feel lighter, maybe a ring
Maybe
or something.
water also. I think I saw
Yeah,
water
water. Yeah,
in your
basically
work.
all the organic compounds, also humans. So you drop much slower than a rock from equal, yeah, maybe steel mass with the equal mass, it would drop much faster. Yeah, and
Is it
well, the
related
most amazing thing is you can actually build a spaceship with artificial gravity using my theory. I forgot to mention that.
Oh
So
yeah. Important one.
if you inflate the mass, if you increase the mass without increasing the number of particles, then you have very little number of particles per kilogram and very little gravity. And so that basically means that your gravitation constant will be very small. And then if you can do that with a spaceship by
Yeah.
using particle accelerators, so all of the walls of your spaceship need to be tiny particle accelerators, inflating the mass of a super dense gas inside, so that the gravitation constant of the spaceship is very small, so that it falls very slowly, but people inside fall normally. So an orbit is basically falling around the Earth. So basically the end result would be that people could walk when they are in Earth orbit.
Okay. Okay. Because the spaceship drops slower.
Slower, yeah. So basically the people
there.
in the spaceship have different orbits. So people
Yeah.
want to go this orbit and the spaceship that orbit, but they're still in the same spaceship, so they're pressed against the
Yeah.
ground. Well,
Oh,
normally a
that's
spaceship doesn't have a floor, doesn't have a ground, but then you could have a spaceship that actually has a floor.
yeah, of course, and that's a very, very outstanding result.
The difficulty is to have you would have to use some heptafluor iodine, some super dense gas, extremely dense gas, because you need to have a gas which is heavier than the tube it's kept in, and it's very difficult. And also to accelerate something like that close to the speed of light is very difficult because of the mean path. You don't want collisions. Normally in particle accelerators, the density is extremely low. It's just a very small
Few
beam
particles.
that's accelerated. So trying to do that with something very dense is gonna be difficult. But that's another project. It's not the chromogravity scale. It's the chromogravity ring. And it would be much more challenging. Probably would need a team of 100 people. Whereas the chromogravity scale will just need 2 people or so.
So we'll see you in the next project then
Yeah.
as
Okay.
well.
Thank you.
Thank you very much, Sky.
Yeah.
My pleasure.
Bye. Yeah.
Good continuation.
Okay, finish the video.
Yeah, you can stop the record. Yeah.
I stopped the recording. No, I think. Did I stop
it and it will save in MP4 somewhere. We have to look for this.
Actually, I just stopped video, but I don't know if I stopped the recording.